Good morning, everyone. Welcome to the workshop Water, Wastewater and Environment, Technology and Culture. Today's workshop is co-organized by the Laboratory of Sustainable Waste Management Technologies of Ελληνικό University and the School of Energy and Environment of the Southest University of Nanjing. On the occasion of today's celebration of World Water Day, it is our particular pleasure and honor to have speakers with expertise in the field of wastewater treatment, biosolids management, and environmental protection practices. Now, the opening remarks of the workshop will be given by Professor Kalvousiotis, President of Ελληνικό University, and Professor Guangchan Zhu. Please, Professor Kalvousiotis, the floor is yours. Thank you. Professor, we cannot hear you.
Dear Professor Guangchan, dear Professor Kokinos, dear colleagues, ladies and gentlemen from China and Greece also, it is with the same joy that our two universities and our two laboratories participate in today's meeting in the context of the celebration of World Water Day. I am indeed truly honored to have you here with us today, and I hope that this day will mark the beginning of a fruitful and enriching partnership that I believe will mark the beginning of a fruitful, that I believe will be highly beneficial to both our universities. When I assumed my duties as president of the Ελληνικό University, one of my first goals was to pursue academic and research collaborations with selected institutions in Asia. And this is because I truly believe in the value of open and distance education and internationalization, as well as the importance of academic collaboration and mobility that can lead to constructive collaborations and activities. In this regard, I thought that working with a Chinese institution with a commitment to excellence, innovation, inclusion and global engagement like yours would be a great opportunity. So we're really happy to participate together in this scientific workshop and to have the opportunity to discuss with you the accumulated experience of all of us during the years of operation of our laboratories. We believe that this experience will be very useful for our further cooperation aimed at joint research projects. So I sincerely highlight today's meeting as I consider this to be an excellent opportunity to discuss issues related to our future cooperation and also to get to know our institutions better. I sincerely hope that we will be able to work together and even consider the possibility of developing a joint research program in a field of mutual interest, as well as continuing research collaborations between our teaching staff. Our two ancient countries, recognizing the importance of cooperation, have signed various agreements on cultural, scientific, and technological issues since 1979. Also, educational cooperation of understanding based on the idea that both Greece and China are friends and share the same ambitions. We must not forget that China-Greece cooperation has always been at the forefront of China-Europe relations, exemplifying flying exchanges between countries of different cultural backgrounds and civilizations to learn from each other. We predict that the future of China-Greek relations seems to be very successful, productive, and fruitful as for both our institutions, the Silk Road that has connected Greece with China since the time of Alexander the Great aims to open channels of communication and cooperation between our countries. And of course, we hope between our institutions, and we believe that we should cultivate our cooperation for the additional reason that the growing Chinese community in Greece is another reason to further cultivate our cooperation. Now, Professor Guakchan is invited to address his greetings to our meeting. Once again, I sincerely thank you for your presence at this very interesting workshop. Thank you very much.
Okay, thank you, President and Professor Yanis. Today is 32nd World Day, and also is the first day of the 77th Chinese World Week. I'm very glad today we can together to discuss some issues, and there will be 3 scholars from university and 4 scholars from our university to make the presentation. I think today's meeting will enhance our understanding each other and can make forward the cooperation in the future. I will thank you again for the past in the past years to make some ideas and cooperation forward. Okay, thank you, Professor Yanni.
Thank you very much, professors. Now we will have our first presentation, which will be given by Ms. Kanderaki, and it is entitled Brief Outcomes of the Degradation Rate of Pharmaceuticals via Cold Plasma for Wastewater Remediation. Ms. Kanderaki, please proceed. Thank you very much.
Hello, good morning. Give me a second, please. Can you see my full screen? Is it okay?
Yes, of course.
Yes.
Okay. Okay. Hello, good morning. My name is Aristis Kanderaki, and I am a PhD candidate in Hellenic University under the supervision of Professor Ioannis Kalabouzotis at the Laboratory of Sustainable Waste Management Technologies. My presentation will be focused on the emerging technology of cold atmospheric plasma for the remediation of wastewater, resulting in the elimination of pharmaceutical occurrence in the environment. 3 pharmaceutical active compounds have been chosen for this preliminary study. Okay, sorry about that. Pharmaceuticals occurrence in aquatic environments are a global emerging issue as they are released from the human body without being entirely metabolized, and they are designed by their purpose to be highly effective at a trace amount. The seemingly ubiquitous presence of pharmaceuticals in municipal wastewater, surface and also groundwater worldwide has been reported in the last decade and more than 80 pharmaceuticals. More than 80 pharmaceuticals have been detected at various concentrations in the range of ppm to ppb. Municipal and hospital wastewater treatment plants are not equipped with advanced technologies to eliminate such emerging contaminants, and conventional treatments via biological and physicochemical procedures do not succeed enough for this kind of micropollutants. On a laboratory scale, though, advanced oxidation processes have been recently bearing interest as effectual treatment approach, showing a good opportunity for environmental cleanup applications. So-called atmospheric pressure plasma belong to the category of advanced oxidation processes, AOPS, and is faced as an advantageous and a promising remediation technique for water and sludge derived from wastewater treatment plants, bearing benefits such as high degradation rate, energy efficiency, and short treatment times. At this point, I feel like I should introduce you more into the term plasma, since most people don't know that plasma is the fourth state of matter, which simply and practically means that plasma is an ionized gas consisting of approximately equal numbers of positively and negative charged particles. The present work investigates the degradation rate of sulfethanoxazole, diclofenac, and trimethoprim. They are the three pharmaceuticals I mentioned before, in aqueous medium using a DBD-based plasma jet. The target were selected due to their frequency occurrence in wastewater and environmental samples. The present work claims the efficient removal of these pharmaceuticals and mainly the progressive degradation over the post-treatment period, i.e. after the plasma action. This fact has important implications towards the advancement of wastewater treatment plants, especially at the face of the activated sludge process. And in this slide, you can see in the third option now, our plasma as an advanced oxidation method. So this is our setup. The DBD-based plasma jet reactor used in this work has been illustrated in the present figure. Briefly, the reactor is fed with controlled flow of helium gas and driven by 10 kHz high voltage during pharmaceutical treatment. A beaker, one at a time, containing the 10 ml of specimen is placed on the grounded surface and aligned with the plasma jet symmetry axis due to a specially designed insulating holder. The plasma jet is thus immersed into the liquid and steers it. Individual stock solutions are prepared by dissolving each compound in methanol at concentration of 10 ppm, and from these stock solutions, working standard solutions of lower concentration are freshly prepared before treatment by simply diluting with deionized ultrapure water to 50 ppb. Which was preferred as a concentration due to the detection records of these pharmaceuticals in wastes. For each batch, a triplicate of each pharmaceutical at a volume of 10 ml is treated. An additional sample is used as control, which is exposed to all procedures but plasma, except plasma. Treatment times of 5, 10, 15, and 20 minutes were applied at predefined treatment conditions. 1,500 microliters of treated and control samples are stored in the vials of LCMS-MS for analysis. LCMS-MS injections proceeded exactly after 1, 3, 24, and 48 hours for treatment, and control sample is also measured in each analysis batch. So, jumping into our results now, these figures summarize the results obtained after treatment of all 3 pharmaceutical compounds for different plasma exposure durations. Namely, this figure shows the dynamic evolution of diclofenac over the first 20 minutes of the treatment, unveiling 2 different reaction rates. A relatively fast one during the first 10 minutes and a relatively slower one during the last 10 minutes. I could try to draw that to be more, but anyway. Notably, a complete degradation of the diclofenac compound is implied. Similar dynamic behavior is revealed for the SMX compound. However, in this case, degradation rates are lower. Despite that, a removal of almost 80% is clearly achieved for the SMX compound. Trimethoprim reveals a completely different case of gradual degradation over time, reaching a level of less than half of the initial concentration. The effect of post-treatment times up to 48 hours are considered for all pharmaceuticals and for all the durations of the actual plasma action, as plotted in these figures. Interestingly, the plasma species induced into the aqueous medium continue to degrade the pharmaceuticals, even for the more resistive to the plasma action compound like trimethoprim. Taking a closer look into the most representative examples, diclofenac is finally degraded up to 68% in contrast to the 30% achieved after 5 minutes treatment. SMX started from 23 to 65, and even trimethoprim, which is a more persistent compound, revealed a 76% final degradation. The most interesting concept of post-treatment should be highlighted, and this is very important finding. Energy may be saved by treating pharmaceuticals for min scale times and allowing for their enhanced degradation over times without any additional energy cost. So, recapping, in the present study, a plasma jet reactor was utilized as a precursor-free advanced oxidation process for the degradation of diclofenac, SMX, and trimethoprim in aqueous solutions, emphasizing to post-treatment evolution. The results indicated high degradation degree for the first mentioned compounds and promising rate for trimethoprim under the present discharge regime and conditions, of course. Thank you very much for your attention, and I am available for questions if anyone wants to ask.
Thank you very much for the excellent presentation. There are any remarks, any questions from the participants? So we may proceed to the next presentation, which will be given by Hin Lee, and is on mechanisms and interactions in a methanotroph's microalgae system for simultaneous nitrogen removal and carbon reduction. Okay, we can see already the presentation.
Oh, hello. Is everything okay?
Yes, but you can
Yeah.
put the full screen. Yes, of course,
Yeah.
the full screen mode. Thank you very much.
Okay,
You may
thank you.
proceed.
Hello, ladies and gentlemen from Greece, good morning. My name is Xin Li. It's my great pleasure to be here to share my research. I'm a PhD student, and my supervisor is Professor Guangchan Zhu and Yongze Lu. My topic today is mechanisms and interaction in a methanol troughs metrology system for the nitrogen removal and the carbon reduction. Let's begin with the background. The wastewater treatment plant is a great invention which solved the sanitation problem. The basic principle of the biotechnology treatment is to convert the carbon, the nitrogen, and the phosphorus into CO2, the nitrogen, N2O, or sludge, so that they can be separated from the wastewater. But in today, the shortage of the resource, the carbon, nitrogen, and phosphorus should be regarded as a resource. So it's better if we can convert them to energy, animal food, and fertilizer. It could be better. So the water resource recovery facility is highly recommended in Europe, US, and in China. Anaerobic biotechnology is the most potential technology for recovery. It can convert the carbon to the biogas so that it can be used for the electricity or heat or other power. But there are several issues needed to be resolved. For example, the biogas, the methane is a biogas only makes up only about 60% of the biogas. The rest is the CO2. And the concentration of the ammonia and the dissolved methane in the effluent is also high in the effluent. It needs to be further retreatment. Microbial engineering is an emerging biotechnology that achieves species function through the assembly of different microorganisms. There are two main approaches. One is the top-down approach, starting from the complex microbial community, enriching and cultivating them in a specific environment. So, and finally, achieve the microbial assembly. The other one is the bottom-up approach, which achieve the assembly by transforming or selecting microorganisms with known functions. No matter which kind of these two approach, you need to go through by these 4 steps: design, building, test, and learn. And you repeat it through the cycle of these 4 steps. You know more about this microbiome, and you can get the function you want to have it. We select 2 kinds of microorganisms. One is the macroalgae. We may familiar with it. Macroalgae could consume the CO2 and produce oxygen, and they reached in lipid or protein. It's regarded as the next generation biofuels. And another one is methanol troughs, also called methane oxidizing bacteria, MOB. It can consume the methane and oxygen and produce CO2. So if we put them together, it could be more attractive. The macroalgae could produce oxygen for the methanol troughs, and the methanol troughs could produce CO2 for macroalgae. So they feed on the biogas, both the methane and the CO2. So they can be used for the treatment of effluent of anaerobic effluent. And we convert the biogas to biomass so that we can produce protein or lipid. Within the framework of the microbiome, we conduct both the top-down approach and the down-top approach. Through these two kinds of research, we deepen our understanding of these two microbial partnership, and then we can build a more effective system through the regional design. For the top-down approach, firstly, we want to build a mob-based sludge to recover nitrogen. And during a long-term research, we use methane as the only carbon source. We found that the intermittent aeration could promote the mob enrichment and the nitrogen removal. And the methanol monas is the most enriched mob during this long-term enrichment. We also found that the simulation is the main way of ammonia removal, and the protein content was also shows the ammonia was intake for protein synthesis. But the ammonia recovery rate is too low in this experiment. So we want to develop a membrane aeration bioreactor, MABR. The bacteria grows faster in this reactor. The nitrogen removal rate was also near 5 times higher than in the previous study. So right now, we have the sludge, which use mob as a substrate. And we try to induce the transforming of microbial population through direct illumination. And we got it. You can see the microbiology is growing by the under the illumination. We successfully obtained this microbiology, and we set up the two-step bioreactor. In the first reactor, it's a co-culture of mob and microbiology. In the second one, it's only the mob. And even this two-stage reactor is developed, but only the first one, the co-culture one, contribute most of the nitrogen removal. And the microbial sequencing also shows that the methanocystis and the synendesmos was the most enriched in this PMBR. So in the first part, we found that the co-culture of mob and microbiology could achieve some surprising result. And in the second part, we want to investigate the interaction between the mob and the microbiology. So we try to use this down-top approach. And the pure culture was carried out in this part. We select two groups. One is a single culture of microbiology, and another one is a co-culture of microbiology and mob. We found that in the co-culture, the microbiology cell density was much higher than in the single culture. But interesting, the chlorophyll concentration was lower. And the microbiology RNA-seq also shows that the gene related to the photosynthesis in the co-culture was down-regulation. Instead of this, some gene related to acetic intake and the TCE cycle was up-regulation. This means in addition to the CO2 cross-feeding, CO2 and oxygen cross-feeding, the mob could also produce some organic compound for the microalgae growth. But we don't know what are they. So in this experiment, we select two kind of methanol traps to employ which kind of organic the mob could separate. By using the NMR, we found that the acetic, formate, lactic, or succinate may be the organic compound, but the concentration is very low in the bench study. So we set up a field bench study. During a long-term culture, we found the acetic and the formate maybe the organic compound from mob, and the lactic and the succinic is only the kind of intermediate products. They could also be resolved. So now we have a much deeper understanding of these two kind of partner. So we know the microalgae is benefit from the partnership. So if we want to utilize this new way to maximize the useful production, we may select the microalgae as our products. So it should maybe it's a lipid or something. So we built a photo membrane biofilm reactor. In this reactor, the methanol traps is only act as a catalyst. They converting the methane to acetic or CO2 to microalgae. And by this way, the thickness of the microalgae biofilm is much higher than in the single culture of microalgae. That means we could get more biomass and we could get more products. Also, the nitrogen removal rate shows the nitrogen could also be removed during a dark cycle. This increases the adaptability of this system. Finally, we want to build a kinetic model of this reactor. In the model, we consider the autotrophic growth of microalgae and the heterotrophic growth of microalgae and the mesotrophic growth. We have some result. For example, on the distribution of the oxygen, it's just like this. The oxygen, the highest concentration of oxygen is near the biofilm. Maybe it's like here. And this work is still ongoing. We hope to use this model to obtain more useful information, such as the optimize of the reactor. So this is the story of these two kind of interesting microorganisms. We believe this will bring a new approach to recovery of resources in wastewater, and we can do more about it. So many thanks for your time and listening. I would really appreciate your comments or suggestions. Okay, thank you. Thank you.
Thank you very much, Mr. Hinley. Thank you. Do you have any questions from the audience, from the participants? Nothing, so we can proceed with the next presentation. Thank you again.
Thank you.
So Ms. Kolkocha now will present the effect of pH, organic matter and clay on the heavy metal soil pollution indices under the influence of treated wastewater and biosolids. Ms. Kolkocha, you can share your presentation.
Thank you very much. Give me just one moment.
Of course. Okay, you can see the
Okay.
presentation.
There, thank you. Okay.
You can put it in a full mode, full screen mode.
We're ready?
We lost the presentation. Can you please share it again or redo it?
Let me try again.
Of course.
Can you see it now?
Not yet. Let's wait. Maybe the
I'm
internet
sorry, give me.
connection is problematic.
If it is too big, you can
Yes.
share your screen instead of the presentation.
I am also trying to do that.
Okay.
Okay, now
You can see my screen.
now we are trying to see the screen. It's starting to share the content.
Okay.
It's on process, so we can wait.
Yes. Can you see the presentation or not yet?
Not yet.
Can you see anything? Okay.
Anastasia, no, we cannot see it, but just give me 2 minutes in order to share it for you.
Okay, thank you.
Anastasia, please send me again the presentation because I cannot find it.
Okay. So I'm sharing right now, but you cannot see anything.
We just can see that you are trying to share your content, but
Okay.
not
I'm sending it again.
Okay, thank you. Okay, I'll try to share the presentation.
You found it?
Yes, I found it.
Okay.
Can you see at full screen mode you have the presentation?
Όταν ενεργοποιήσει επεξεργασίας πάνω.
Το έχω πατήσει.
Από πάνω δεν το πάτησες, όχι. Ενεργοποίηση επεξεργασίας. Το κίτρινο στο κίτρινο, από κάτω λίγο πιο κάτω.
Δεν το βλέπω.
Στην κίτρινη μπάρα, λέει προστατευμένη η προβολή.
Ναι, σωστά.
Θα τα καταφέρουμε.
Okay. Sorry for the technical issue. This is happening.
Okay. So good morning, ladies and gentlemen. My name is Anastasia Kolokotsa, and I am a PhD candidate in the university, in Ελληνικό University, with Professor Kalabriziotis. And in this presentation, we're going to discuss the effect of pH, organic matter, and clay on the heavy metal soil pollution indices under the influence of treated wastewater and biosolids. Okay, next. Okay. We performed an experiment in the island of Zakynthos with the aim to study the interactions between the aforementioned soil physical and chemical properties and the soil pollution indices, and in particular, heavy metal load, elemental pollution index, total concentration factor, and the pollution load index for the evaluation of soil toxicity, since the three properties influence greatly the fate of the heavy metals in the soil. Next. pH is a factor that greatly affects the various processes in soil. Solubility, bioavailability, and translocation of heavy metals from soil to plants varies due to pH changes, and their mobility through soil has been reported that it increases in acidic conditions. Researchers have reported a negative relation between pH and heavy metals in soil, so when soil pH increases, the binding ability of soil decreases as far as metals are concerned. Also, it affects the complexation ability of organic matter and clay particles. Organic matter, on the other hand, is an umbrella term that includes organic constituents of soil, such as undecayed plant and animal tissues and others, and its composition is determined by environmental conditions as well as human activities. It has a very high absorption capacity and cation exchange capacity, and can bind heavy metals and create chelate compounds. The complexes between organic matter and heavy metals can affect their solubility, bioavailability, and mobility. Finally, clay refers to various hydrosilicates of aluminum, magnesium, or iron, and can also bind heavy metals, frequently due to their negative charge. Their adsorptive properties and widespread availability make them excellent agents for soil remediation, and some have been used as soil improvers, such as bentonite. In the next slide, next. Thank you. Next slide. Okay, thank you. In the next slide, we can see the four exam pollution indices how they are calculated. M is the concentration of the metal, CF is the concentration factor. And in order to assess these indices that we calculated, we use the proposed critical pollution indices levels as proposed by Papayon and al. The next slide, please. Okay. The experiment was conducted in pots in a greenhouse and included 12 treatments in 4 repetitions based on a randomized block design. We used simulated soil, and that was achieved by adding sand, organic matter in the form of biosolid, heavy metal mixtures, and calcium oxide. The heavy metal mixtures were added to the treatments after first sampling, and the scope was to create definite and equidistant characteristics in the soil properties that would allow us to investigate the effect of soil heavy metal pollution. We irrigated the soil initially with fresh well water, and then for the remainder of the experiment with treated wastewater from the local wastewater treatment plant, according to the setup of the experimental design. The metals that we examined were zinc, manganese, copper, cadmium, cobalt, chromium, nickel, and lead. You can move to the next slide.
There's a bit delay. Just wait.
Okay. I'm waiting.
Okay.
Okay. We performed 5 samplings in total, and we analyzed the results through regression analysis. And in particular, we studied the interactions between pH, organic matter, and clay with the 8 metals, as well as the interaction of pH, organic matter, and clay with the pollution indices. You can, the next slide. Okay. In this slide, we have the mean concentrations of heavy metals, the mean values of the pore indices, as well as the soil properties from the experimental data per sampling. We can see that after the addition of the heavy metal mixture in the second sampling, the heavy metal content and pollution indices decreased over time by the end of the experiment, apart from the case of manganese. Next. The regression analysis revealed several statistically significant interactions between heavy metals, pH, organic matter, and clay, and resulted in equations that were used to calculate the theoretical values of the heavy metals from these interactions. As we can see on Table 2, most of the interactions among organic matter, clay, and heavy metals were synergistic, while the interactions of pH and heavy metals revealed mostly negative regression equations. By subtracting the actual heavy metal concentration from these theoretical values, we calculated the contribution of these interactions to the metal concentration in soil. On Table 3, we can see the maximum contributions of various interactions in every sampling, and by calculating the mean for each metal, the combined effect of pH, organic matter, and clay on that metal. The highest contributions due to the interactions for zinc and manganese were found in the fourth sampling, while for the rest of the metals in the second. Next. The next slide, shows the results of the regression analysis between pH and HML. On Table 4, we can see the regression equations and below the resulting diagrams. In all 4 samplings that the interactions were statistically significant, the relation was antagonistic. On Table 5, the qualitative results are shown. The pollution levels were calculated according to the table from Papayoannou and all, and the percent frequency of each category was calculated. The results showed mostly optimum levels of pollution. Once again, the regression equations were used to determine the theoretical values of HML and due to its interaction with pH. By comparing the actual HML to the theoretical, there weren't significant changes as far as soil pollution was concerned. Still, according to the Table 6, the arithmetic values of the theoretical HML varied greatly in respect to the actual, and in the case of the fourth sampling, there was an increase of 263%. Next. As far as the interaction between pH and EPI is concerned, we have statistically significant relations in 4 of the 5 samplings, and only in the first 2 of the relation is antagonistic, and the third and fourth synergistic antagonistic. In this case, the prevalent actual pollution levels were determined as high, and the theoretical values followed the same trend. The highest percentage change was found in the third sampling, where EPI was increased up to 448%. Next. The pH and PLI interactions were similar to those of pH and EPI, antagonistic initially and then synergistic antagonistic. The pollution levels were predominantly high in Table 11, and there were no significant differences between the actual and theoretical levels. In this case, the highest increase was in the second sampling, where the actual PLI value different from the theoretical by 408%. Next. Okay. The interaction of pH and TSCF were antagonistic in nature, and the pollution levels were determined as high in most cases. In the fourth sampling, there was the highest increase by 262%. These previous cases revealed that as the pH increased, the indices lowered, as shown by their antagonistic interaction. This was expected as pH and heavy metals had a negative relation. That relation carried over to the interaction of pH with the indices. Next, thank you. Next, we're going to continue to the interactions of organic matter with the pore indices. In the case of organic matter on HML, in the first and fifth sampling, the relation was synergistic, whereas in the second and fourth sampling, it was synergistic antagonistic. And in the third sampling, the regression analysis did not reveal a significant relation. In most of the treatments, the pollution levels were judged as optimum, and there is a difference between the actual HML levels and interactive levels in the fourth sampling. On table 17, the actual pollution levels varied, while the interactive levels were 100% optimum. The highest numerical increase was in the fourth sampling by 524%. Next. The organic matter and EPI interaction were synergistic, except in the second sampling that was synergistic antagonistic, and there were no significant differences between the actual and theoretical pollution levels. The largest increase was in the third sampling by 714%, and this was the highest difference that we saw in the experiment. Next. Organic matter and PLI interactions were synergistic, except again in the second sampling that was synergistic antagonistic, and there were no significant differences between the actual and theoretical pollution levels. The largest increase was by 688% in the third sampling. Next, we have organic matter and TCF, where in the first and fifth sampling, the relation was synergistic, and in the second and fourth was synergistic antagonistic. Again, in most treatment, the pollution levels were high, and there wasn't a difference between the actual TCF levels and the interactive levels. The highest numerical increase was in the fourth sampling by 524%. Okay, next. And finally, we're going to take a look at the interactions between clay and the pore indices. And in this case, clay and the HML revealed the synergistic antagonistic relation in the first, third, and fourth sampling, while in the second and fifth sampling, it was synergistic. The pollution levels were mostly optimum and did not yield any major differences between actual and theoretical levels. The maximum percentage increase was in the third sampling, where the theoretical HML value was 333% higher than the actual. Next. The interaction between clay and EPI was synergistic and antagonistic in most of the samplings, except in the second that it was synergistic. Again, the pollution levels were high, and there is a difference between the theoretical and actual levels in the fifth sampling, where the frequency of high pollution levels are greater than the theoretical calculations. Where the frequency of high pollution levels were greater in the theoretical calculation, and they were 91.7% in respect to the actual that was 79.1%. The largest percent change is found in the third sampling, where the theoretical EPI value was 475% higher than the actual EPI. Next. Okay. The regression analysis of clay and PLI revealed the synergistic antagonistic relations in the first, third, fourth, and fifth samplings, and synergistic in the second. The pollution levels in the fifth sampling, the pollution levels were mostly high, and once again, there is a difference between the theoretical and actual levels in the fifth sampling, where the frequency of high pollution levels were greater in the theoretical calculations in respect to the actual. The largest percentage change is found in the third sampling, where the theoretical PLI value was 426% higher than the actual PLI. Next. Clay and TCF revealed synergistic antagonistic relation in the first, third, and fourth sampling, while in the second and fifth it was synergistic. The pollution levels were mostly high, and there is a difference between the theoretical and actual levels in the fifth sampling again, where the frequency of high pollution levels is greater in the theoretical calculation in respect to the actual. The maximum percentage increase was in the third sampling, where the theoretical TCF value was 333% higher than the actual TCF. Once again, we saw that the increase of organic matter or clay increases the pollution indexes, as shown by their synergistic interaction. This was once again expected, since organic matter and clay and heavy metals had a positive relation, and that carried over to their interactions with the indices. Next. In conclusion, The interaction among these three factors, pH, organic matter, and clay, and soil heavy metals can affect the heavy metal content in soil, as well as the pollution indices, either by detracting or adding metal content. Most of the interactions of clay and organic matter with heavy metals were synergistic in nature, while the interaction of pH with heavy metals was antagonistic. In accordance to these findings, the pollution indices showed similar relations to pH, organic matter, and clay. pH had a negative relation with the pore indices, and an increase of pH led to a decrease of the indices, whereas organic matter and clay had a positive relation with the indices. Soil heavy metal content decreased over time, and there are signs of soil amelioration. Finally, further analysis can be performed in order to assess the impact of other interactions, such as nutrients and heavy metals, as well as heavy metals and heavy metals, and how this interaction may affect soil toxicity, as expressed by those pollution indices, as well as soil fertility, since several of the heavy metals act as micronutrients. Thank you very much for your attention. If you have any comments, I'm here.
Thank you very much, Anastasia. Again, we're very sorry for the technical issue. Do we have any questions about Anastasia's presentation? We're still on time, so we can proceed with the next presentation, which will be given by Ling Gong. And the presentation is about preparation and characterization of adsorbent by simultaneous enrichment and slow release of nitrogen and phosphorus in anaerobic fermentation biogas slurry. Please, Ling Gong, you may proceed with your presentation.
Okay,
hello, nice to meet you.
Thank you.
We cannot hear you very well.
Okay, can you see my?
We can see your presentation.
Okay. So,
okay. Just check your microphone because we need to hear you louder than now.
is okay now?
Yes, it's better. Thank you very much.
Okay, thank you very much.
Thank you.
Okay. Good morning, maybe in your country, and I'm great honor to share part of works about the resource reuse part works of the preparation and characterization of absorbent for similar enriched and slow release of nitrogen and phosphorus in anaerobic fermentation by gas slurry. And I will make my presentation from the next 5 parts. As we all know, nitrogen and phosphorus are very important elements in the structure and functions of living organisms, but these imports will cause a eutrophication, which will threaten drinking water safety and the biodiversity of aquatic ecosystems. So a lot of people just to prevent phosphorus and nitrogen pollutions and increasing strict discharge standards have been comprehensively implemented in wastewater treatment plants worldwide. However, there is one thing should pay attention to, that phosphorus resources are different from nitrogen, which we can generate naturally. Phosphorus resources are cannot generated from the naturally, so it's really resources we should to pay much attention to, because if just with following the current mining rates, it will just be depleted in 15 or 100 to 100 years. And we need to pay attention to that. Actually, absolutely in China, the main sources of nitrogen and phosphorus pollutants are urban life, from urban life and rural life, runoff from farm and farmland livestock breeding. And we all know that the wastewater from urban life will be just sent to wastewater treatment plants, and they can be just effluent. But we pay much attention to that the phosphorus are caught in excess sludge, which can be aerobic digested with farmland livestock breakings or manures from the farmers. So we have we just pay attention to that, and the aerobic digestrations, we can find the biogas can generate the electric and its energy ways to get the gas away. But the slurry is not pay much attention to. However, nitrogen and phosphorus and other nutrients are almost stored in the biogas slurry. And we just summary nutrient competitions in the biogas slurry. We can find that the ammonia and total phosphorus are very high in the biogas slurry. And the nitrogens, the most important is ammonia nitrogens, and the phosphorus are dissolved total phosphorus. In theory, nitrogen phosphorus and other nutrients animals of the aerobic fermentation raw materials are stored in the biogas slurry, which can fertilize the crops. However, there are a lot of technologies of biogas slurries treatment and resource utilization, and we need to pay attention to that. If we just direct to effluent it, there is a limited limited copper of soil digestion, which will lead to the farmland runoff and groundwater pollution. Besides, there also have some heavy metals and antibiotics in the biogas slurry, and there are potential safety hazards in direct use. Besides that, even somebody may say that we can just choose them, but the nitrogen content of the biogas slurry is very high, and the carbon nitrogen ratio is very low, so that there is a difficult and will cost a high cost of different treatment of discharge. So we biogas slurry for nitrogen and phosphorus enrichment and recovery after processing discharge is an ideal has become the focus of related fields. So when we can find that resource recycling technology, there are a lot of stuff and field memory method, but the how some it's a little difficult to get resources back. So we just find another, just focus on the another common method is the desorption method. This method is most important is lie in the performance of adsorbent. The absorbent of large adsorption capability, wide source of raw material safety and non-toxicity, and should have good compatibility with soil. So here. And so we, based on the ideas, we just an analysis is commonly used adsorbent. We find that there are friendly adsorption material can be efficiently enrich nitrogen and phosphorus in biogas slurry is zeolite and bichar. So after that, we also note the analysis the adsorption principles of nitrate and ammonium nitrate and phosphorus, so that we can make some modification methods with the adsorbent. So we based on the bichar, and we need to find the semi-mineral enriched nitrogen phosphorus by regulating nitrogen phosphorus supporting slow release soil amenities can be formed for the field use. Besides, so that based on this, we just choose here. We just choose to share about the rice hull raw material, which is very common in Chinese countryside, and with that, we also find that because the nitrate and the phosphorus, so we use another is LDHS, and to modify the in the rice hard raw material bichar. So here is about four different materials. And as we can see, the LDH is modified. We can find that it's like a sandwich, and the inside is onions. So where is the phosphate adsorption in? And this is also another is a structure of the way we make it. And after we how the materials, and we did some test of it. It's about adsorption isomers and model parameters. According to the data, we can find that the modified LDHS RHBC can get about 3 times more than RHBC, and we can find that the chorus scalar of R of Langmuir model was 4 and is much higher than the friendly isomers. So we can find that Langmuir model can better describe the adoption and cultural process of the phosphorus. And besides that, we also did the adsorption kinetics curve and kinetic modeling fitting parameters. We can find also that at about 200 minutes, nearly 1.465 milligram per milligram of phosphorus, about 66% was calculated, and the equipment was reached about 3 hours. And we can find that in order to further capture the effect of phosphorus structure of LDHS IPC, we just do the interparticular diffusion is here, and this perf diffusion is here. We cannot just go to the 0. We can find that result shows that the line relationship is multi-line without passing through the origin of the graph. And this is also something about the with LDHS to adsorb nitrate, and we can also find the similar things, but we must pay attention to that. With LDHS, RHBC can get the master about 56.66. Besides that, we also use the true bypass slurry, which is catch from the farm in Nanjing, operating normally for more than 3 months, and the actual bypass slurry was born in color. As you can see, when the dosage increased from 0.5 to 15, the removal rates of ammonium nitrate totally showed an increasing trend. And when the dosage is about 2.5 gram per liter, the removal rate of the total phosphorus is stable, and then it may be about just stable at 18%. Yeah. Besides that, I will also find some of the photo of the graph settings because we choose some great gas seeds and to test whether it is possible as a fertilization to make the seeds to grow up and be grow up. After an incubation of this, length of remaining choosing 10, you can see seeds were determined with a mineral scalar for stability analysis. And we also, when we find the experiment results are good for the bypass slurry to reuse. So we also did some another things such as the characterizations about such as the isoelectric point. We can find that this is the pH value of bypass slurry. It is about 7.19, and we can find that the modified BC, the LDHS BC is higher than this one. So what that means that when the initial pH is we can find if the solvent in the liquid are charged, positive charged, which means it can catch more phosphate. And this is just to take some things because we need to know phosphate and nitrate and chlorine and sulfur did have some competitions with absorption of phosphorus. We can find that it's not so much because it's just stable, maybe 9. And before that, we also do some regenerations. We can find that after about 3 times, this absorption cannot touch the initial performance. Then we did some NCMEDS. We can find that this is RH, and there is a logic technical section of the word is observed here. And this is IHBC spectra. We can find a lot of micros in these places. This is LDHS. This is LDHS HBC. We can directly find that the LDHS are aggregated in the micros of the biker very real. And this is XRD. It's also just when we want to from this, and we can find that absorption about at the 2 theater about 32.7. We can find that there is a digest feature cross the structure during high temperature. So we can find this is BC. And after that, we also can find some characteristic LDAH diffraction planes. This is about the 1, 2, 3. Yes, we observed here. So what does this mean? Means that the LDH's layers are very well adhered to the biture, and what make a great performance with the absorption of phosphorus. And this is SMDS. We can also find the same LDH presentation from the solution onto the BC. From LDH BC, we can find that the iron and the magnesium are adhered very well. And after the absorption, we can find that the chloride is layer and the phosphate is up. Yes, and if so. This work can advance the state of that environment-friendly phosphate reclaim. Importantly, this pressure enhances LDH spares absorptions of phosphate by 3 times versus pure LDH particles. This phosphate lender absorptions have potential to be used as a slow-release flotation. There are also some potential problems such as stable abilities and the technical and economic analysis models of the actual large-scale application probably is not perfect. So in the future, maybe we can explore, to make more efforts to verify the stabilities of the absorbent. And by the way, we can just to do under accurate field conditions and large-scale experiments and field valid will be carried out to evaluate the environmental importance of the sovereignty in the utilization of agricultural resources. Yeah, that's it. That's all about my share. Yes, thank you very much.
Thank you very much. Very interesting presentation, very beautiful presentation. So we may have one question from Professor Kokinos. Yes?
Thank you very much, Link, for your very interesting presentation. I was thinking of some questions, but your last slide covered my thoughts. But I would like to just a small clarification on the slide. You had the grass, the length of the grass. You used the if you go there at that slide, because we ran some similar experiments and I was interested. Yes, this one. No, the next one. The grass. No, the one with the photo of the grass, the length of the grass seeds. Yes, this one. You used moistened seeds with 0.1 gram of biochar samples. You have done some previous experiments to use this value, this amount of biochar samples. I mean, 0.1 was in dispersion or on a solid basement where the seeds were grown.
You mean that it's just in the adsorbent or with the oil together?
No, I mean, how you end up with this amount of the biochar samples, and if the biochar was floating in water or it was on wet paper, for example, because we use wet paper as a basement, as a growth medium. I'm trying to understand the experimental setup.
I'm sorry, maybe you...
Where you cultivated these seeds and how you used this amount of biochar.
Yeah, you mean that how well did I get the seeds?
Yeah.
And how it just buy it for online. And then we just to make it with the soil together with the half to half, 5 to 5, and then just set them in, and we just give them the same temperature and same light in the lab, and then to choose it, and then after about 10 days, and we can find them, and we just cut them, and we to take the photos and to get the names of them and to compare. Yeah.
Okay. Thank you.
Thank you. Thank you.
Thank you very much. Now, Professor Kalavousiotis will award an honorary prize. Please, Professor Kalavousiotis.
Okay, thank you very much, Akavi. We chose today at our international meeting to honor our partner soil science researcher, Prodromos Koukoulakis, the scientist who is actively involved in our research efforts of the last 20 years. His contribution was valuable and essential in every important step of the development of our laboratory, starting from our presence in Agrinion until today. For these many years of sincere, essential and effective contribution, we honor him today, hoping that he will always continue to contribute to our laboratory with his scientific experiences. We thank him very much for all his contribution. Ευχαριστούμε πάρα πολύ για όλη τη συνεργασία, η οποία είναι πολύχρονη, διαρκής, πολυερκής και διαρκής. Και θέλω να το περιμένω. Ναι, θα βγάλω, θα περίμενε, γι' αυτό υπομονή. Υπομονή. And for this, Πρόδρομος Κoukoulakis.
Την κάμερα λίγο πιο ψηλά, παρακαλώ, για να μπορούμε να βλέπουμε καλύτερα την απονομή. Πιο ψηλά, πιο ψηλά. Ευχαριστούμε.
Φαίνεται όμως αυτό εδώ. Βγάλε εσύ πρώτα και μετά εδώ. Και εδώ, αυτά εδώ. Κάτσε φωτογραφίες, εσύ το ίδιο. Συγχαρητήρια. Εκεί, κοιτάξτε και λίγο εκεί. Πρόβλημα τον Έλλη.
Shall I speak in English or in Greek? Κύριε Πρόεδρε, είναι τιμή μου να αποφασίσετε να με τιμήσετε με το σπουδαίο, ας πούμε, βραβείο. Με στηρίζετε, διότι απλά αναγνωρίζετε το έργο, την προσπάθειά μου που έχω καταβάλει όλα αυτά τα χρόνια και αυτό για μένα αποτελεί ηθική ικανοποίηση. Και το καλύτερο βραβείο είναι αυτό για μένα. Ευχαριστώ πάρα πολύ.
Συγχαρητήρια.
Ευχαριστούμε κύριε Πρόεδρε.
Υγεία και χαρά πάντα.
Είστε καλά.
Και προόδους εδώ στους εγγονούς.
Το ίδιο εύχομαι και στα παιδιά και στον Κωστάκη. Να είναι πάντοτε καρτσιλιάδες.
Thank you very much. Ekavi, please to continue.
So thank you very much, Professor, for this very short ceremony, for honoring the researcher, Mr. Koukoulakis, for his long and very important research activities and help in our laboratory. So after this small break, we can proceed with the next presentation by Biao Yang. His presentation will be about rapid self-hydrolysis in concentration process and anaerobic digestion efficiency of iron-based flocculated sludge. Mr. Biao Yang, can you please proceed with the presentation?
Hello everyone, can you see my voice?
Can see you, but not your presentation yet.
Okay, I will put my presentation.
Okay. Okay, perfect. Oh, I'm sorry. I skipped a presentation, but we will do it after Mr. Biao Yang's presentation. I'm sorry. Okay. Let's see the presentation at the full screen mode.
Hello professors, friends and everyone. I'm honored to share with you some of my work on anaerobic digestion of carbon capture sludge. My presentation will cover the following aspects. As well known, traditional wastewater treatment processes result in very high carbon emissions. By calculating the carbon emissions of 5 conventional wastewater treatment processes, we have found that conventional wastewater treatment processes typically exhibit high carbon emissions, with indirect carbon emissions being the primary contributor, accounting for 99%, mostly originating from electricity consumption. In fact, wastewater contains a significant amount of resources and energy. The Amsterdam wastewater chain resource recovery strategy has identified resources that can be recovered from wastewater and categorized them into 6 value tiers, and suggests that the value of recovered resources is directly proportional to the recovery costs. From the representative wastewater treatment consumption plants in various countries, we find that carbon capture from wastewater will become the future direction of wastewater treatment development. The significance of carbon capture is that the concentrated liquid obtained after carbon capture contains a large amount of organic matter from the origin wastewater, processing higher organic chemical energy. The carbon capture process mainly includes 3 methods. The first one is a chemical method, using primary enhancement processes to achieve the sedimentation of particles in wastewater. The second one is biologic method, enhancing biological flocculation and sludge absorption by increasing influent load. The third one is physical method, separating organic compounds from wastewater using membranes with selective emission functionality. By comparison, the chemical method has better prospects due to its lower costs and a smaller footprint. Therefore, we have chosen it to investigate the methane production events of sludge captured through the primary enhanced chemical processes. Firstly, we have screened a promising capture agent called CBHYC. It is the mechanism of synthesis of ion-based covalent complex flocculant. We connected the metal salts and organic components together with the chemical called VIA slime coupling agents. Through a large number of experiments, we have discovered amino functional slime exhibits the best capture effect on COD in wastewater treatment. CBHYC has better capture efficiency for SCOD compared to ferric salt, with a maximum COD capture rate reaching up to 78.7%. At the same time, CBHYC also has an effective removal of phosphorus, achieving compliance for phosphorus levels when dosages exceed 60 milligrams per liter. By the FTIR mass analysis, we find that CBHYC demonstrates a favorable removal efficiency for carboxylic acid cyclic compounds and aliphatic compounds. CBHYC also can effectively capture anionic surfactants represented by LAS. After the organic matter capture was completed, we allowed the sludge to settle for a period of time. During this period, we observed some changes in the properties of the captured sludge. Lower dosages of capture agents result in higher sludge concentration factors, while CBHYC carrying organic components exhibit higher sludge concentration factors. As the concentration time increases, the captured sludge gradually undergoes self-hydrolysis. Initially, the COD content in the sludge rapidly increases, followed by a gradual decrease, while the COD in the supernatant gradually recedes. The increase in animal nitrogen can prove the hydrolysis and the release of the proteins. This phenomenon is quite interesting, so we speculate that it may be attributed to a change in the form of ion. During the concentration and the hydrolysis process, we found that the travelling ion is rapidly reduced to the equivalent ion. This indicates that ion obtained electrons from organic matter, leading to the degradation of the organic components. Due to the lower ion content in CBHYC compared to ferric salt, all the ion captured by CBHYC in the sludge can be converted to the developed ion with a short period. Also, due to the CBHYC's faster ferric ion reduction process, it facilitates the easier release of the phosphorus from the captured sludge. After that, we carried out anaerobic digestion of the concentrated sludge. We found that at different dosages, CBHYC exhibits a constantly higher methane yield compared to ferric salt in capturing sludge. In-column ratio experiments indicate that higher in-column ratios favor an increase in methane yield while reducing CO2 generation, thereby enhance the methane purity. During anaerobic digestion, there was no significant observation of the massive organic matter soluble dilation combined with the rapid generation of the methane observed. These results indicate that the hydrolysis phase and the acid phase proceed almost synchronously. Through the analysis of the microbial community structure, we found that as the dosage of ion increases, the relative abundance of functional microorganisms responsible for consuming VFA decreases, such as commander disease. This indicates that the residual ferric this indicates that the residual ferric salt in carbon-rich sludge enhances sludge acidification performance. However, the impact of CBHYC on such microorganisms is lower compared to ferric salt. At low dosage levels, CBHYC treated sludge exhibits higher abundance of methane-producing bacteria, particularly estolastic methanogens. This suggests that the sludge captured with CBHYC as the capture agent has higher methane production efficiency. Above is my presentation. Thank you, everyone.
Thank you very much for your very interesting presentation. Anybody in the audience has any questions? Something that wants to underline, mention, maybe? Okay, thank you very much again. So now Mr. Rabadzis may proceed with his presentation about common production practices and cultivation techniques of main crops of Greece, olives, grapes, strawberries, kiwis, and vegetables, as a potential source of microplastics in the soil ecosystem.
Yes, hello. Do you hear me?
Yes, we can hear you perfectly.
Okay.
We can see your presentation.
Okay, perfect. My name is Christos Arabatsis. I'm also a PhD candidate in the Laboratory of Sustainable Waste Management of the Hellenic University. I would like to say good afternoon to the colleagues in China and also good morning to the colleagues here in Greece. Mainly with our presentation, we want to inform you about the work that we are planning and doing also in the Laboratory of Sustainable Waste Management regarding the microplastics in agricultural soils. We all very well know that over the last 70 years, the use of plastics in agri-food system and food value chains has become pervasive. The features of plastic, like the low cost, the adaptability, and the durability, made them crept into every part of our food chain. Soils are one of the main receptors and reservoirs of agricultural plastics and are known to contain larger amounts of microplastic than the oceans. So there is an increasingly demand from the scientific community to see what is happening with the microplastics in soils and also how this is the things with the leakage of microplastics in the other parts of the environment. From the agricultural sector, the sector of crop production and livestock are the largest users, accounting for 10 million tons per year collectively. And then the sectors of fishery and aquaculture, they are following. Now, regarding the plastic debris is frequently categorized into subgroups based on particle size, distinguishing between microplastic, mesoplastics, and microplastics and nanoplastics. Now, mainly in our cultivation practices, we can find plastics in agriculture in the form of mulching films, tunnels and greenhouses films and nets, irrigation tubes and drip lines, bags, silage films, bottles, and various others. Now, our work has mainly to do with our important crops of Greece, and I would like to give you a brief note regarding the main crops in Greece. So, one of the biggest crops in Greece is the olive cultivation. Greece is the world's third largest producer of edible olives and olive oil. Olive trees, they are spread all around the country, and we have about 160 million olive trees. And the annual production of olive oil is about 300,000 tons. And the 90% of this production of olive oil belongs to the category of virgin olive oil. That makes Greece the world's first producer of virgin olive oil. And also we have about 200,000 tons of table olives. Then another important crop of Greece is the strawberry cultivation. This accounts about 70,000 tons of strawberry. 90% of that strawberry, these strawberries are exported to third countries, and we mainly find these cultivations in the areas of Western Greece, in Etolokardania, Achaia, and Ilia. Another important crop of Greece is the Chinese gooseberry, kiwi. Okay. Although kiwi is coming from the Great China, Greece is the third producer and exporter of kiwis in the world. And we produce around 300,000 tons of kiwis in Greece, and 2/3 of that production is exported in third countries, among them also in China. Also, we have an important cultivation of table grapes and an important cultivation also of greenhouse vegetables. That it is focused mainly in the islands of Creta and in Peloponnesus. So, our work regarding the correlation of microplastic pollution and the most common cultivation techniques of our important cultivation in Greece has to do with the following. The identification of specific farming practices applied to important crops in our country as potential or non-potential sources of microplastics, and in addition, the development of a methodology for the development of a forecast model of microplastic pollution in rural areas of the country. And this has to do mainly with the fact that if we run or if we go to the international literature, we will see that mainly the studies are focused to mulching, to sewage sludge, compost addition, and slow control released fertilizers. So we see a gap regarding specific practices and their work as a source of microplastics. Now, regarding the production of olive oil, one of the most important steps in the production line of olive oil cultivation is the harvesting of the olive fruit. Here in Greece, we are a relatively small country, and we cannot apply mechanical harvest of olive oils because the farmers they have orchards that they are very small in size. So we are harvesting olives only with humans and in the old traditional way by using harvesting net, mating of polyethylene, and also harvesting plastic fabric made from polypropylene. And in your picture, in the slide, you can see the nets and the fabric that we are using and the way the harvesting is made. You can realize that these materials, they are applied to the soil and then they are crushed or they are stressed by the farmers. So this might cause a leakage, let's say, of microplastic to the soil. And if we imagine that this is a technique that we apply for over 40 years, that means that probably we will be able to find, let's say, a large amount of microplastic in olive groves, in the soil of olive groves. Also, we have some olive groves in Greece that they are in slopes, or the geography is such that we cannot, let's say, harvest the fruit immediately. So in that case, in these cases, we apply permanent bedding nets made from of polyethylene. And we are expecting and we are waiting for the fruit to fall naturally by through ripening or air, and then the farmers, they go there and they pick up the fruits. Another important part of olive cultivation is that after we have finished with the harvesting, we use plastic bags in order to transfer the produce to the olive mills. Okay, so also this step can act as a source of microplastic in the soil. Then we have the strawberry production. Okay, here we have the classic mulching of strawberries in order to protect them from various pathogens and weeds, and also to promote early growth. Okay, and also low tunnels made from polyethanol in order to be able to plant earlier and also to protect our strawberries from the climatic conditions. In kiwi production, mainly here in Greece, we are using the anti-hail nets made from polyethylene. And also this is the case with the production of table grapes. Furthermore, in specific regions of Greece, like Corinthos, we are applying also plastic covers, plastic films to our vineyards in order to protect the production and also to expand the production further deeper in September or in October, and to have a better income for the farmers. And finally, in greenhouses around the Mediterranean region, we are using a technique that is called soil solarization. This is a technique that we use on October and September. These are the months with a lot of sun in Greece. And we cultivate the soil, then we apply water, and then we cover with the plastic film in order to pasteurize the soil and to protect our future plantations from various soil pathogens like fungi or bacteria. Now, here you see the sampling sites This is the map of Greece, and you can see the sampling sites from different areas of Greece that these cultivations are important in that areas. And then after the sampling, we have after the areas, we have the sampling collection. Regarding the strawberry fields and greenhouses, we're using the method developed by Dr. Isaris from our laboratory. For soil samples of olive groves, table grapes, and kiwi groves, we are using the method described by Ying Sue and Fleury 2021. In order to have a statistical based collection of the sample. The sampling depth is 10 centimeters, and we totally collect a sample, a composite sample from each orchard of 2 kilograms. We also have included in our sample collection the climatic and soil maps of Greece in order to exclude any bias regarding soil structure and climatic conditions. And also we are taking measures in order to prevent sample contamination by plastics. Now, regarding the method of working in the laboratory in order to extract the microplastics, we are using the sodium chloride flotation method, as described also by Dr. Isaris of our lab. And basically, we are taking 150 grams of air-dried soil. Then we are doing flotation with sodium chloride. And after that, we have a final step of the filtrates with hydrogen peroxide in order to, let's say, digest the organic matter. Regarding the instruments that we are using, basically we are using FTIR ATR, Fourier transformation infrared with attenuate total reflectance. And the expected results will be that we will understand the contribution of our common cultivation practices in the soil pollution of our fields and orchards. We want to be able to modeling microplastic pollution in major agricultural region of Greece. Since you have already saw the samples are taken from all over Greece, we want to have a cartography of microplastic pollution of Greek agricultural soils. And furthermore, we want to identify more sustainable and microplastic-free cultivation techniques and materials. For example, sacks from or nets from fibers of plant source. Finally, we want to be able to inform our farmers regarding the cultivations that they apply in order to go in the future in a more friendly techniques regarding the microplastic pollution. So I would like to thank you for your patience and also for listening to me. And I am open for any kind of question. Thank you.
Thank you very much for this very interesting presentation. We can understand that you're at the beginning of your PhD research. So we're expecting these very ambitious experiments and interesting results. So we may proceed with the next presentation by Mr. Michalopoulos. Thank you again, Mr. Rabatzis. So the next presentation will be about technology and regulatory risks as critical factors for the use of treated wastewater in an urban environment. Okay.
Hello to all.
Perfect.
Can you see my presentation in full screen?
Full screen mode, not yet, but we can see it.
Now?
Yes, of course. Thank you very much.
Okay. I would like to thank you for the proposal to be in this meeting as a presenter. Hello to all of our colleagues in the China and Greece. I will make a presentation. I'm Sotiris Michalopoulos. My name is Sotiris Michalopoulos. I am a PhD candidate in the laboratory of sustainable waste management technologies. And my presentation has a title, Technology and Regulatory Risks as Critical Factors for the Reuse of Treated Wastewater in an Urban Environment. This is a common work with the professor and president of the university, Mr. Kalabrousiotis. As major causes, the water stress, the fast-growing populations, I'm sorry. I'm trying to minimize a pop-up window. Okay. I thought that the water stress, the fast-growing populations, and the climate change effects means countries that struggles to provide their people with sufficient clean water. The reuse of treated wastewater offers multiple new opportunities, but as an unconventional water resource, its use faces many challenges that need to be clearly defined and addressed. In this context, a series of factors influencing the reuse of treated wastewater is set, on which the recording and analysis of their characteristics is considered necessary both for the implementation of circular strategies for water, as well as for defining the limits and the parameters for safe and successful reuse of treated wastewater in an urban environment. We are talking about an urban environment and not for irrigation. The circular economy has a central role in this approach, maximizing the value derived from water, process, and practices. Some of the factors mentioned are the financial mechanism, the security issues, the energy issues, the social acceptance issues, and also the public information issues. In these presentations, two of the factors will be examined, shows their importance on enable a shift from conventional to unconventional water resources. These two factors are the technology and the regulatory risks. We're starting with the technology. Technology is a critical factor in the reuse of treated wastewater in an urban environment. It refers to the pace and adaptation to technological change. It is evaluated based on its ability to provide specific quality standards on the final product, means the recycled water, based on specific priority objectives that use it for holistic assessment and optimization of wastewater management. The appropriate choice of technologies for such approaches is perhaps the most critical design decision, as they involve the development of new processes, innovative tools for the design of distribution networks in the urban area, new processing techniques with improved effect on potable uses, and sanitary and environmental safety with no risk for the ecosystem. The structure of an urban water supply ecosystem must also have control mechanisms with spatial characteristics, fact that favored by the transition of cities towards to the smart way or smart era. There are many parameters that must be monitored depending on the reuse category of the water. The quality of the analysis and the evaluation of the data of these parameters are considered important in both risk management and successful planning. In the way to assess the technology options, to meet the required quality standards for their use within cities, several key aspects must be considered. The most important of these includes the technology assessments, the software for trend analysis, the specifications of further development or support, the technical applications of the monitoring processes, and the regulatory standards support capability. More specifically, first of all, is the automation and remote monitoring that nowadays incorporating also AI features, enabling real-time monitoring of the water quality, the flow rates, and the whole system performance. This leads to more efficient operations and faster response to any problems. Second is intelligent sensor networks, providing valuable data for the process optimization and the compliance monitoring. Indicative parameters are the pH, the dissolved oxygen, the turbidity, and the nutrient levels in the treated wastewater. Third are the technologies and specifications of the systems that use it in decentralized treatment facilities that are being used more and more in our days due to their economical and more environmentally sustainable treatment process. An assessment and evaluation process of such systems technology could drive to reduce pressure on the central infrastructures. Fourth, various technologies concerning data collection, gathering raw data from various sources, data mining to find patterns in the data we have and thus trends in the end user's behavior, or data analysis that will contribute to any decision process. Fifth is the pilot testing technologies to determine the effectiveness, the reliability and safety of treated wastewater prior to use in the urban areas. Sixth is the life cycle simulations, some life cycle simulations for the projection of a comprehensive view of the environmental footprint and the sustainability of the technology that will be provided. And now we'll talk about the regulatory risks. The regulatory risks are the risks of implementing a policy option or a subsequent change in laws governing the water, the guidelines and the policy issues of the reuse of treated wastewater. The regulatory frameworks that has been developed over the time are being accompanied by an urgent need to continuously evolve in order to keep up with the current trends. This will drive to mitigate risks and ensure safe. Thus, it is important for any government to monitor and be informed of such changes in regulations, standards, and directives that may affect the reuse of treated wastewater. An additional important parameter is that the adaptation to any new regulatory requirements may involve additional costs or modifications to the existing infrastructure and practices. To conclude, water management is a complex issue that requires a framework of rules and regulations to govern its operation, as any solutions are highly dependent not only on local conditions, but also on challenges related to institutions and policies. Thus, each country should review, advance, and adapt its policies in ways to achieve a smooth and effective transition from non-use to reuse of treated wastewater, and show how the water cycle is governed at a local and regional level. The path to this transition will certainly hide various obstacles and challenges of multi-level governance. For instance, while technical solutions may suit different situations, the institutional framework is likely to differ. Thus, ideally, the approach for each governmental institution or stakeholder must benchmark possible solutions that complies with it. Many times also, the ambitions or the facts of national and regional politics either differ or are in the direction of low expectations. This risk results in time delays, outdated technologies, and lack of compatibility with all these parallel actions. Therefore, organizational change, systemic approaches, and cooperation by which the interested parties develop and assess this risk must be the foundation for strengthening the multi-level governance of the water. As these actions could contribute on the exploitation of the issues of the reuse, the actual process should also be considered as a connected link of different sectors that complies with the regulatory rules. Thank you very much for your attention.
Thank you very much, Mr. Michalopoulos, for the very useful information about regulatory risks. Thank you.
Thank you.
So we may proceed with the next presentation from Mr. Eite Kabalach about boosting volatile fatty acids production from sweat sludge anaerobic fermentation by a novel hydrolytic bacteria pretreatment. Mr. Kabalach, can you please share your presentation?
Sorry. Just
We can wait for a few minutes until you are ready. We are on time.
And you can take your computer to I think.
Perfect, we can see the presentation.
Okay. It's my pleasure to see you.
Perhaps a small sound issue. We can hear your voice twice. Maybe you should turn off the microphone from the room and just have open the microphone from your computer.
Hello?
We cannot hear you clearly.
You can speak up louder. Why?
Maybe if you use headphones, it's better.
Wait a minute. Zoom. Yes. Hello?
Not so clear, but we may proceed.
Unclear. Okay, present from other place. Conclude. Please finish.
You can take your computer to my office. Yes, yeah.
Oh.
Professor, this is and the eight suitable place to start his presentation. So, okay.
Do you want from us to proceed with the next presentation until then you can solve your technical issue?
I think he will come in minutes. So we just wait.
Okay.
Okay, okay.
Okay, now we can see the presentation.
Okay.
You hear me?
Okay, yes, we hear you, we hear you. Okay, you can start, thank you.
Sorry.
No problem.
Yeah. Good morning. Good morning, Professor. It's my pleasure to see all of you, Professor. My name is Gaballa from Egypt. I am a postdoctor under Supervisor Professor Zhu Zhuangsa. My research area focus on produce like organic acid or biogas production from wastes, undertaken boosting volatile fatty acids production from waste activities large anaerobic fermentation by a novel hydrolytic bacteria pretreatment. The research background, the environmental sound economically disposal of the waste activities large has become significant challenge with the rapid rise of urbanization and industrialization raising widespread public work. Reports indicated that China produced more than 55 million tons of waste activities sludge annually. This was leading to serious environmental problems like foul odor, like pathogenic bacteria. The harmless treatment of waste activities as well the harvesting valuable resources, renewable energy from waste activities has been widely accepted as an effective treatment to solve this problem. Up to now, anaerobic fermentation has been considered as a promising strategy to the disposal of waste activities sludge, which could effectively convert valuable resources like carbohydrate, protein into high value product like volatile fatty acids. However, the extracellular volumic substance that surrounds the organic substrate in waste activity sludge may greatly reduce the efficiency of sludge fermentation. For this reason, it's important to find a practical strategy to improve EBS disruption, which may boost the ultimate volatile fatty acids production. To speed the breakdown of waste activity sludge and enhancing the generation of volatile fatty acids, multiple studies have demonstrated in pretreatment strategy can dissolve the cell wall and EBS structure. Among them, biological pretreatment has been valuable advantage, including less energy consumption, less anaerobic fermentation inhibitors, more environmentally friendly process, and less expensive on operation. The primary usage of biological pretreatment is to increase the rate of hydrolysis by various enzymes like alkaline proteins or microorganisms like bacteria, which have emerged as a promising strategy for enhancing volatile fatty acids production. However, to best knowledge, it's still an open question the effects of hydrolysis bacteria pretreatment on solubilization, hydrolysis, and the microbial community. The research objective studied the novel hydrolysis bacteria pretreatment on hydrolysis solubilization toward improving organic acid generation from anaerobic digestion. Also, the change of microbial community structure during the accumulation of volatile fatty acids has revealed by hydrolysis bacteria for waste activity sludge pretreatment. The finding has been obtained in this study may help to develop a novel and effective methods to change fermentative volatile fatty acids production from anaerobic digestion of waste activated sludge. My experiment out the substrate I used waste activated sludge or the secondary sludge from wastewater treatment plant and then pretreatmented by hydrolysis bacteria before anaerobic digestion start, and then studied the effect of hydrolysis bacteria on during solubilization stage and the hydrolysis stage and the acidogenesis stage. During the solubilization stage, I studied or I analyzed the soluble chemical oxygen demand and soluble protein, soluble polysaccharide, and EEM. And during the hydrolysis stage, I analyzed the ammonia content and the enzymes activity. This table illustrates the characterization of inoculum which used on the experiment and the substrate. This is my treatment or I used different hydrolysis bacteria concentration. First group I used direct addition. I add the hydrolysis bacteria with different concentration direct. And the second group and third group, I treatment the waste activity sludge first before anaerobic digestion start at temperature 35 and 50 degrees Celsius for 6 hours with different hydrolysis bacteria concentration. The condition of the experiment during anaerobic fermentation was batch anaerobic fermentation, and the ratio between the sludge and the inoculum 5%, and I used the reactor 5 milli was working volume 360 milli, and the experiment is continued until 7 days and temperature 35 degrees Celsius and 120 RPM. The analytical test during the experiment, I analysis soluble chemical oxygen demand and the polysaccharide and the protein to determine the characteristic solubilization efficiency. And also I test EEM will determine at 1 day from start the experiment to determine the biodegradability of released soluble substance. And the total volatile fatty acids, I will test it every day. The result and discussion for first stage, the solubilization stage or the degradation of the EBS, which surrounds the waste active sludge. The release of organic matter from the sludge come from two parts: the disintegration of EBS and the disruption of cell membrane. To clarify the disintegration of cells and EBS, protein and polysaccharide, soluble protein and polysaccharide are the main component of EBS structure. Thus, the effect of different hydrolysis bacteria concentration on the EBS structure was investigated by analyzing the change of soluble protein and soluble polysaccharide and soluble COD. From the chart, we can see the hydrolysis bacteria enhanced the solubilization of protein and polysaccharide and the soluble chemical oxygen demand compared with the control. Also the enhanced increase the hydrolysis bacteria concentration. The highest soluble protein and soluble polysaccharide and soluble chemical oxygen demand have hydrolysis bacteria 8%. The second chart illustrates the hydrolysis stage 2. I test the enzyme protease and the glycosides and the ammonia content as indicators to hydrolysis stage. From the figures, we can see the hydrolysis bacteria enhanced the ammonia content and enhanced the protease and glycosides compared with the control. Also the highest ammonia content and the protease and the glycosides was on the treatment of hydrolysis bacteria 8%. The last stage, acidogenic stage, means the production of volatile fatty acids. From the chart, we can see the highest volatile fatty acids production happened from hydrolysis bacteria 8%. We can see around the 718 milligram per gram volatile suspended solid. Also the hydrolysis bacteria enhanced the individual organic acid like acetic acid or propionic acid. From the chart, we can see the acetic acid and the propionic acid, the highest organic acid from all of the acids. In conclusion, the result showed that the solubilization and the hydrolysis efficiency as a limited stage were improved by the hydrolysis bacteria techniques. From the chart, we can see the soluble protein and the soluble polysaccharide concentration increased from 136 and 42 milligram per liter on control to about 3,261 and 388 milligram per liter with different hydrolysis bacteria dosages respectively. Also, volatile fatty acids were increased on range of 1.5 to 40.17 times more after hydrolysis bacteria pretreatment, more than the control only raw waste activated sludge. Thank you, Professor. Question and correlation are welcome.
Thank you very much. Do we have any questions or correction as you were writing? Okay, thank you again. Thank you, Kevin, very much for your excellent presentation. Thank you. Now, the last presentation of this short workshop is about improving soil fertility through the combined use of earthworms and biochars. Unfortunately, Dr. Grilla cannot be with us today, so I will give this presentation by myself. Let me share it. Please tell me if you can see it at full screen mode. Are we okay? Thank you. So, my name is Isaria Kavi. I'm a postdoc researcher at the Laboratory of Sustainable Waste Management Technologies of the School of Science and Technology of Ελληνικό University. I'm a chemist, and today I will introduce you to the project of BioCom. BioCom is about improving soil fertility through the combined use of earthworms and biochars. This project is co-founded by Greece and the European Union in the frame of Agricultural Development Programme 2014-2022. But before I start with the main goals and the research results of this project, I would like to say some few words about our laboratory. Our laboratory has as a main mission to develop technologies and actions in the framework of sustainable waste management, with ultimate goals of protection of natural resources through the reduction of the direct disposal of biosolids in the environment and its utilization as a soil improver and compost in agriculture, wants to strengthen the bioeconomy through the development and production of new innovative products from municipal waste management, and also has already developed a software, a decision support system, in order to use it for waste reuse. So here you can see the steps, the stages in order to achieve our goal, which is the determination of micropollutants, of course the quantification of them by using analytical techniques, the treatment of the micropollutants with innovative techniques in order to reuse biosolids or wastewater for sustainable reasons, for sustainable purposes actually, in the context of environmental sustainability. So briefly, here you can see the research topics of our lab, which are wastewater and biosolids management, identification of microplastics, control and evaluation of soil and cultivation, reuse of treated wastewater in agriculture, and detection and treatment of pharmaceuticals. Some of these topics have already been mentioned by previous speakers, which are members of our team. The main members of our team are, of course, Professor Kalavriziotis and Associate Professor Dr. Kokinos Petros, Dr. Grill and Dr. Papaioannou, the PhD candidate Ms. Kanderaki Alkistis, myself, and a researcher, a very important member of our team, Mr. Kiritsis Spiros. So, let's talk about BioCom. BioCom, as I told you before, wants to improve soil fertility by using earthworms and biochars in order to produce nutritional and agronomic value products. This implementation will be at the pilot stage. So, their partners in order to achieve this project is Ελληνικό University, is the Technical University of Crete, and particularly the School of Mineral Resource Engineering, 2 enterprises, the Bioorgan and Think Smart Ike enterprises, and 2 agricultural cooperatives, the Agricultural Cooperative of Missolonghi Navpaktias, the Union, and the Agricultural Olive Cooperation of Agios Apostolos. Now we will see the 3 main pillars of our project, which are research, innovation, and extroversion. Let's begin with the objectives of the research. At the first stage, we did design, construct, and operate a pilot-scale bioreactor. Particularly, the Bioorgan enterprise designed the bioreactor that you can see at the picture. The bioreactor will operate at the optimum conditions of aeration and will try to fermentate barren soil using earthworms at the first stage, and on the second stage using earthworms and also biochars. So, about biochar production, we will have 2 different types of biochars, the biochars type A and B. The biochars type A are coming from the burning, the pyrolysis at 360 Celsius degrees of olive pruning, and the biochar type B came from the pyrolysis of sweat sludge. Here you can see the pictures of the 2 different biochars, and also you can see the specific surface area that the University of Crete has determined. At the third stage, we evaluated the barren soil of barren soil that is cultivated systematically by strawberries in order to use it as a substrate for cultural cultivation of spinach in a greenhouse at the next stages. So we did take a sample of barren soil and we measured the organic matter, which was 2%. Also, we determined the main heavy metals that you can find in the sample, and from these values we estimated the EPI, the Environmental Pollution Index, using our decision support system, and we found that we have no pollution indication, but we have a low percentage of organic matter, maybe near to the normal values. So after the evaluation of the barren soil, we have to operate fully the bioreactor and of course fertilize the barren soils with this combined action. Also, we have to construct small greenhouses in order to conduct our future experiments. As we can see here, we have already constructed small greenhouses that can be moved. So then, after the fermentation process, we have to evaluate the humic content of the barren soils. And of course, we have to conduct, as I said before, the greenhouse experiments that will take place 2 times per year for 2 years using spinach as seeds. Here is the decision support system for wastewater and biosolids use that we have already used in order to estimate the EP index, and we will use in the future also in order to understand how is the optimal dose of nutrients, the recommended dose, and the method of application for fermentation, and also to estimate again the pollution load index. So, the last stage of a BioCom project is the evaluation of the horticultural cultivation at the laboratory with analytical methods, and of course the techno-economic assessment in order to understand the market needs to use organic soil conditioners. I would like now to move to the second pillar of a BioCom project, which is the innovation and the actions that must be taken. The actions firstly is to apply innovative practices for sustainable intense agricultural production in order to develop a technology in pilot scale that can fertilize barren soils using these modified organic wastes. And all this action will give us the creation of a cooperative scene. Then we'll go to the dissemination pillar, which is the creation of a website that you can see here, and you can go and find information about the Biorecording project. And also you can find us at social media accounts. In the context of dissemination, we have already shown our work at workshops and exhibitions, and we're planning to go to agricultural exhibitions, conferences, and scientific journals in order to disseminate the results of this project. Thank you very much for your attention. I hope in the future that I can provide you with more results, because now we're at the beginning of this project. But we found it interesting to present you the idea and the main target of this research project. Thank you very much. Now, after my presentation, you may proceed with the closing remarks. Professor Kalavuziotis or Professor Guakchan, you may close this nice workshop. From my part, I would like to thank all the participants for the presentations and, of course, their scientific contributions at the field of environmental sustainability. Thank you. Professor Kalavuziotis, please. We cannot hear you, Professor. Κύριε Γιάννη, δεν σας ακούμε.
Thank you very much, Akavi, for your very important presentation about the experiences in our lab to present. Thank you to Professor Guakchan also with the Chinese colleagues about for this important workshop today. And before to finish, it is very important and fruitful to discuss Professor Guakchan about the new opportunities the new opportunities for our research in our two laboratories. I remember that 1 year ago went to visit your lab in Nanjing to present a project. And for this project, it is very important to discuss, if you prefer, about what doing now in the near future. Okay, the floor is yours. Thank you very much. I have my presentation, but it is the same presentation to present 1 year ago in your university. Thank you very much.
Okay, thank you. Yes, thank you. Today we are happy to go to the 9 recorded presentations. I think everyone can get many information from the presentation, and every presentation maybe will be research results, and I think the presentation should be the beginning for us to communicate again. And actually, the most of the presentation focus on the research about the soil agriculture waste and so on. Most of the research also focus on the quality of the nutrients from the wastewater. I think that this is a common research project. So in the future, we can continue to discuss and next year and discuss the chance of cooperation to research together. So thank you, guys, and thank you all. Okay.
Thank you very much.
Thank you. Professor Guangchan, if to last year to discuss in your university about the objectives in our new research, maybe to explore the potential of exploiting rural influence from animal units by products from anaerobic digestion of organic waste and liquids, to investigate the effects of these bioproducts on plant growth, soil quality, environmental quality, and crop productivity. The third is to develop and apply innovative technologies and methods for the treatment of wastewater and biosolids by removing their heavy metal and pharmaceuticals compounds also, and to contribute to the development of a circular economy and bioeconomy in our respective regions and countries by reducing waste generation, etc. These important objectives, I think that to discuss and to wait your decision about this in the future. And thank you again.
Okay. So I think that this year the summer school should be called again. The summer school program.
So, sorry, we have no good connection now, and I don't hear very well.
I'm sorry, there must be a problem with your microphone, probably. We cannot hear you at all.
I mean, it's just summer. We will have the summer school again. Sorry. We have summer school.
So we maybe find a chance to discuss if we can hold a program during the summer school program.
Can you catch?
Okay, Guangchan, please, we have the very good connection now. This is a problematic this time, but for this reason, to finish this fruitful workshop, and then to send you again a letter to discuss about these important things and subjects for our research. It's okay for you?
Yeah.
Okay.
It's okay.
Okay. Many thanks for all. the participants. Thank you very much. I think it is a very, very important workshop today between our two labs because we have the opportunity, all our researchers, to know the topics and subjects about our research. Thank you very much, and many greetings to China, to Nanjing.
Okay, thank you
very much.
Thank you. Goodbye.
Thank you.
Hello, bye.
Hello, bye-bye. Next year or this year to wait in Greece, Bakchan.
Yeah, I will have a chance to.
Okay, many
see you.
greetings.
Yeah, in Greece or in China.
Έλα, Χάβη, Σωτήρη.